I know I've been given the tough task of standing between you and the peak Bangalore traffic. So I'll just try to make this as engaging as possible. How many of you are from an aerospace background in the room? Yeah, other than my colleagues. All right. Okay, my name is Jayanth. I'm a senior director for data science at GE Aerospace. The topic that I'm going to cover today is from concept to sky, transforming aircraft engines with AI. If I may know, how many people actually flew into Bangalore to attend this conference in this room? Awesome. So just to give you some statistics, every 2 seconds, there's an aircraft which is powered by GE technology which is taking off somewhere in the world. It's actually quite remarkable that as I speak, there are close to 900,000 people who are being transported safely to their destinations. And every 3 out of 4 takeoffs are being powered by an GE engine today. So just as a reference, in 2023 alone, there were close to 3 billion people who were transported safely to their destinations by GE engines. I just want to give you a perspective of the GE business before I jump into the AI content. So GE is currently a global leader in GE Aerospace. We have 2 P&Ls. One is the commercial engines and services and defense and propulsion technologies. We are a $32 billion company. 24 billion comes from commercial engines, and about 9 billion comes from the defense. So as you can see, majority of the money that is coming in from services, right? 70% of the services revenue is from commercial services. And then if you look at 55% is coming from defense and systems. So GE essentially makes money by servicing engines, right? And not only by just selling engines. So just switching gears, if we were to look at the data science team, so we are close to 90 data scientists across 5 different countries in the globe. We are located at India, China, UK, the US, as well as Mexico. We have a classic mix of domain experience as well as AI ML. There are a good bunch of people who have a computer science background, and there's also a good bunch of people who have a background of sound engineering as well as AI. So what do these data scientists do? So if you were to look at the application of AI within GE Aerospace, there are plenty. It could be services engineering, where we want to predict which engine is going to come to an MRO shop at what point of time. It could be engineering design, where we want to accelerate the way AI is applied so that we can come up with the best design possible in a quick time frame. It could be finance, where we're looking at predicting the free cash flow for the company. Or it can be supply chain, where we want to look at what should be the right inventory that we need to maintain throughout the year. But my focus for today is going to be specifically on fleet management, right? What I'll take you through over the next few charts is how fleet management is operating today and how we are applying AI to it. There are a bunch of circles that you're seeing here, right from data acquisition to intelligent data. Then we look at engine health monitoring, how is analytics used to maintain the engines. We look at application of image analytics, and then we jump into Gen AI. So the entire presentation is going to be heavily outcome-based. So all of this, what you're seeing on the left-hand side of the page, is going to translate into 3 things. Shop visit management. Since there are close to 44,000 engines which are flying, if an engine is coming to the shop, can we predict which engine is going to come to the shop at what point of time? So once an engine comes to the shop, the next thing that we need to look at is work scope management. The engine itself is huge, right? How do I know which one to be serviced? Should I service the turbine? Should I service the compressor? So work scope management is a key thing there. And finally, the inventory management. Do I have the right part at the right point of time? So let's say an engine is coming to the shop, and I don't have a spare part to go and plug in. The engine is just going to be lying idle in the shop. So that's another area where AI is playing a key role. So if you look at each of these circles, I'm going to talk quite a bit about conventional AI. We're going to talk about machine learning and so on. And as we are progressing clockwise from data acquisition all the way to non-conformance, you'll see that the complexity of the AI models will also go up. So let me jump into data acquisition. So every time an aircraft takes off and lands, we get data in our systems. And there are two kinds of data. One is called snapshot data, where we get data at periodic intervals during the aircraft mission. The second one is continuous engine operations data, where we get data every few seconds from the aircraft engine. This data is then parsed and then stored in cloud so that we can look at operations, we can look at the asset information, and there are several hundreds of analytics which are being orchestrated within the cloud environment. The outcome from the analytics eventually flows into applications. A very common one is an intelligence dashboard. But we also look at how can we monitor some of this in a continuous fashion. So GE has been pioneering this for close to 30 plus years. And there are close to 44,000 engines which are being monitored 24/7. So now that we have the data, so what do we do with that information? So as you see, you have raw data coming in from the sensors, and it would probably look like the graphic that you're seeing here, the red dots. What we've done is we built something called as a gas path digital twin. In simple terms, like you and your friend buy the same phone, the way you operate your phone versus the way your friend operates the phone is going to be very different. The gas path digital twin is nothing but a personalized twin for every engine which is there in the field today. It does two things. One, convert all of this raw information into something which is interpretable, like what you're seeing on the chart there. You do have those blue dots which follow a nice pattern. The second is the gas path digital twin gives me information at various stations within the engine, which is important for me to take critical decisions. A decision can be what is going to be the health of my turbine, what is going to be the health of my compressor. The reason why that becomes important is I want to connect this back to the 3 KPIs or CTQs that I'm trying to address. If an engine comes to the shop, I don't want to rip open the entire engine, but I want to know which part to be serviced. And that's where the gas path digital twin comes in handy. So 2 key CTQs, as I called out, it helps to identify the trend in the data intelligently. It also helps in coming up with module level of health, right, for the GE engine. There's another way where we can use the raw data which is coming in from the sensors. So as and when these data is coming in, is there a way where we can forecast what will be the future sensor value of a given engine? For that to be done, we need to forecast the route structure first. So let's say that there's an aircraft which is flying from Chennai to Mumbai, and over the last few months it's been taking the same route. We look at the probability of that aircraft flying the same route over the next few months, and we predict what could be the potential routes that aircraft can take. Based on that information, we come up with forecasted sensor parameters. The sensor parameters are then stored in the data lake, which could be used for predictive analytics. This information, as you would have realized by now, is extremely nonlinear, right? It's hard to predict what kind of environment an aircraft is being exposed to constantly, and thereby the sensor values which are coming out of the engine. Similarly, the way a customer operates an engine A versus another customer operating the same engine could be very different. It's analogous to two people riding the same bike very differently, subject to various conditions. So this technology actually helps in predicting the nonlinear characteristics, and it forms a key input to predictive analytics. So if I were to jump to engine health monitoring, as I told you, there are close to 44,000 engines which are being monitored 24/7. And we've converted some of the raw data into something which is more interpretable. So in this example that you're seeing, there are close to 18 different inputs or signals which are being fed into my anomaly detection model. It's a multi-dimensional space, and as you can see, the green color circle highlights healthy data, the red color circles highlights anomalous data. So this gives me a probability of the issue which is actually happening, and once that is verified or validated, we provide a recommendation to the customer through a report. One thing which I want to highlight here is, this is a classic example of human-AI cooperation. So as you can see the three arrows, there are three areas where human intervention is needed or present. First, the human is going to validate whether the inputs which are being fed into the model is right or wrong. So once the machine learning model or the anomaly detection model gives me an output, we ensure that the parameters coming out of it make sense. If not, the feedback loop is provided to the model. And third, once the output comes out of the model, the subject matter expert reviews and determines appropriate action before we share the report with the customer. So this is a tried and tested approach. It's been in the field for 10 plus years now. And we have seen that we've been able to provide a 60% improvement in the lead time to identifying certain anomalous behavior. We've been able to increase our detection rates by about 45%. And also the false alerts have gone down by about 50%. So shifting gears, I just want to take you through the analytics-based maintenance. So if you were to look at this chart, the x-axis represents cycles. In simple terms, one cycle is a takeoff and a landing. And what you see on the y-axis is the distress or the wear and tear that a component experiences while it's in flight. So on the bottom left side, every circle that you're seeing here is an engine which is there in the field. And you notice that when all of them are introduced, all the points are clustered together. And as they start accumulating cycles, you see that there is some kind of divergence in the pattern. The red circles have more rapid distress compared to the blue circles, which are a lot more slower in terms of distress compared to the other ones. So this requires a need to establish some kind of a threshold in order to drive an action plan. And that's where AI comes into play, to see how we can define those thresholds for a given engine or a family of engines, so that we take an action well in advance and share that information with the customer. So this is, again, a proven and tested methodology. We have demonstrated 50% decrease in disruptions for an international carrier. The number of decrease in overall has come down by about close to 15%. And there has been a significant increase in terms of utilization as well as the fleet stability. So all of this that you were looking at so far was data which we were getting on wing, right, which is coming directly from the aircraft engines. There is also data which we get off wing. When an engine gets into the shop, we do a lot of videos through borescope, and there are also images which are taken of the components. The objective here is to identify if the health of each of these components is intact or not. If not, can we flag it? So the top left corner that you're seeing is actually an input video. And this is a video which is coming in from one engine. And there could be several thousands of videos which need to be analyzed by the individual in the shop. So if you look at the video right in the middle, you would notice that the frames are color-coded. What it means is we have an AI algorithm which is running in the background. It has the ability to assess the health of each blade in that, from that engine. So when it's green, it says that the blade is healthy. When it's red, you need to watch out. And if you see this exclamation mark, it says that the blade is actually distressed. This is going to be really challenging for an individual in the shop to keep looking at it and then come up with an outcome. Time and again, the consistency is going to become a challenge. And that's where AI comes into play, where we've been able to accelerate some of these outcomes through the image analytics. If you look at the graphic on the top right, you would notice that to the human eye, you would see the blade view, which is on the top left. And then a defective blade will look like that. Whereas if you pass this to an algorithm, it would clearly point out that the blade is defective, where you see the red highlighted region. So this becomes extremely critical. It provides us with increased accuracy. We've been able to demonstrate significant consistency improvement, and it has also reduced the inspection time for all of these components. What I'm showing is only an example of one of the components. There are several thousands of components within an aircraft engine, and this algorithm comes in really handy for executing some of these. So I just want to highlight one example of how generative AI is being used. Let's imagine a part which is coming into the shop, and the part doesn't meet the specifications. There's a non-conformance. What we typically do is compare that part with some of the manuals that we already have. We pass it through a large language model. The large language model tries to compare it against similar examples in the past. And this goes to the subject matter expert from a validation standpoint. And this is what we call as candidate recommendation. And there are two possible scenarios. The output from the LLM is in sync with what the subject matter expert wants. In that case, we proceed with the next steps. The other outcome could be the feedback coming in from the subject matter expert has to be passed on to the LLM so that the next time I have a similar scenario, we have a better prediction. So one thing to note, and I just want to call this within quotes, is we've been using AI in combination with the subject matter experts, right? We have not got to a stage where we want to automate it, considering that safety is our prime CTQ. There will be involvement of subject matter experts or human beings in taking decisions which are coming in from the AI models. This is, again, a tried and tested approach. It's automated the existing process. We've shown significant improvement in terms of productivity. And it actually does a great job in terms of providing the responses where the subject matter expert is able to validate some of these very quickly. So as I come to the end of this talk, I just want to leave you with one thought. As you saw in the circle, we started off with diagnostic AI, then we moved to predictive kind of AI, and then eventually jumped into prescriptive AI. So one thing which I strongly believe in is using the right model for the right problem that we have at hand. We don't need a complex model for a very simple problem. And that's how we've been using AI in GE Aerospace. And this is the last slide which I want to cover. Based on the experience that we've had with the AI in aerospace, two key takeaways. Adoption is a critical endpoint. You might have fascinating models, you could have LLMs, you could have Gen AIs, and so on. But at the end of the day, if nobody is adopting it and taking decisions, the business is not going to see the impact. The core of all of this is the data. You need to have the right data and the infrastructure to support it. Without that, we won't be able to get to the end outcome. Thank you. Open for questions.